Let's start the afternoon session. So we are happy to have Yi-Nan Wang from Peking University, who will tell us on updates on the 4D F-theory landscape. Please, let's welcome him.
Okay, so thanks, Professor Luis Apollo, for the introduction. And today I'm going to talk about actually a review of the recent progress of the exploration of 4D F-theory landscape in the past 10 years, and also present two upcoming works I'm now currently doing with my students. Okay, and this is the outline of the talk. First, I'm going to give a brief introduction to the general concepts of string landscape and F-theory. And then I'm going to review the results and upcoming work on the study of 8D, 6D, and 4D F-theory geometric landscape. And for the second part of the new result, I'm going to present this new Monte Carlo approach for an exploration or probing of the whole set of the so-called 3D-based polytopes in type geometry. And finally, I will mention our recent upcoming work on the computation of massive spectrum in F-theory. So first, the general paradigm of this talk, the whole picture, is a string landscape versus swampland kind of program that has been mentioned, that has been introduced by Professor Cameron Waffen and Timo Wagen's talk last week. So basically, the idea of swampland is saying that not every IR effective field theory would have a UV completion as a quantum gravity theory. And if there exists a consistent, if there exists a consistent QFT in the low energy scale, however, it cannot be embedded into a UV complete quantum gravity theory, then you will say that the theory should lie in a swampland, called swampland. On the other hand, if a theory can be embedded into a UV complete quantum gravity theory or even string theory, we will say that it lies in either the quantum gravity landscape or the string landscape. And of course, as we know, string theory is already a well-defined, sort of well-defined, not very rigorously, but well-defined notion of UV complete quantum gravity theory. So at least we know that for all the string compactification model we get from string theory, that will lie as a subset of the whole quantum gravity theory landscape. And then also, one ultimate goal of this swampland program is to prove the result, so-called string universality. It is saying that maybe in the future, maybe like in 100 years, if you can prove that the string landscape is exactly equal to the quantum gravity landscape, then we can achieve the proof of string theory even without any direct experimental evidences. Because if you can say that all the consistent quantum gravity theory lies in string theory, can be realized using a string theory, then that's equivalent to proving string theory. Okay. And so this is the ultimate goal, I think one ultimate goal of the whole swampland project. Okay. So to achieve this goal, there are two different ways, different approaches to proceed. The first one is to find new swampland conjectures physically, and this approach is good because it's more physical, and these new swampland conjectures could even apply to general quantum gravity theory that's not in string theory. However, in general, it's very difficult to prove these swampland conjectures really rigorously in mathematics. A lot of them are still conjectures. That's the name. And on the other hand, the other way to proceed is to try to expand our known string landscape. Because, as I mentioned before, basically any string compactification will give you a UV complete quantum gravity theory on its own. And if you can proceed in this second direction, you can also get some new hint on what are the new swampland conjectures that put over a constraint on our set of quantum gravity. Okay. And in this talk, I'll mostly talk about review the F-theory landscape. And in general, if you want to build up a string landscape of many, say, 4D or higher dimensional supergravity solutions, then we have to pick a particular version of string theory, and that will include these five different versions of supersymmetric string theory, and also, more interestingly, the strongly coupled version of string theory, including M theory and F theory. So M theory can be thought as a strongly coupled limit of type 2A, while F theory can be thought as a strongly coupled version of type 2B. So in this talk, I will be focusing on F theory. And the one advantage of F theory is that it can realize the largest currently known ensemble of 4D flux vacua. There's a famous number 10 to the 270,000 in my paper with Wang Taylor about 10 years ago. Yeah. So this is one advantage of F-theory, generally speaking. And then I'm going to give a very brief overview or review what is really F-theory. As I said before, F-theory is a strongly coupled version of type 2B. So now I'm going to first review the basic ingredients of type 2B. So in type 2B string theory, we know that there are following stable D branes without spatial dimensions, like D-1, D1, D3, D5, and D7, which can electrically couple to this RR sector tensor field with different degree of forms. And a very important complex scalar field in type 2B is the so-called axial dilettante field, whose real part, so this is a tau field, whose real part is a C0 with an axion, a zero form real scalar in type 2B, while the imaginary part is related to the dilettante that is, corresponds to the string coupling, type 2B string coupling as GS equal to e to the phi. Basically, tau equal to C0 plus I over GS. And as we all learned from the string theory textbook, the type 2B superstring is invariant under the SL2Z S duality, which acts on the axial dilettante field tau as tau goes to A tau plus B over C tau plus D. For instance, there's one particular S duality is to choose, for instance, C0 equals to 0 and maps tau to minus 1 over tau. Physically, it means that we can map the string coupling GS to 1 over GS while still getting an equivalent dual description of your type 2B string theory. And this is a basic result, which is also mentioned in Professor Phil Sang's talk about a more mathematical rigorous proof of a topological twisted version of string theory. Okay, and then in type 2B, there's a very peculiar object, which is a 7 branes. Now for a 7 brane, I mean that the number of spatial dimension is equal to 7, while there's also one time and direction. Hence, a 7 brane is actually a codimension 2, a real codimension 2 object in our 10-dimensional type 2B string theory, and just like a point on a plane. And you can of course go around a point on a plane, and interestingly, if you go around a 7 brane, then we will find that axial dilettante field tau could undergo an SL2Z monodromy after you going around a loop. For instance, as I mentioned, sometimes if I go around this loop around certain kind of 7 brane, then you can map the string coupling GS to 1 over GS. In this sense, in many these kind of 7 brane configurations in the background, there are actually no weakly coupled type 2B limit. And we really need to imply a more powerful geometric technique, a framework of so-called F3 to really describe this kind of very complicated configuration of type 2B superstring theory. Hence, in a short sentence, what is the definition of F3 is that it can be interpreted as a strongly coupled version of type 2B in presence of a lot of these 7 brane in our background. And this F3 itself actually does not have a well-defined, well-studied string worksheet description. Because it's a strongly coupled, there's no perturbative expansion of that. All right. Then what is the geometric definition of F3, which is very interesting, also has a lot of relevance to algebraic geometry. As I mentioned before, so we have a type 2B. So the geometric definition of F3 is to put type 2B on this product space. It's a Minkowski, d-dimensional Minkowski space-times direct product, some kind of base manifold for simplicity. And the power of F3 is that we can choose this manifold B where the strings propagate, where the strings live in, to be not Calabi-Yau. So it doesn't really need to obey the Calabi-Yau condition, and we can still get some kind of supersymmetric Sugra solution. So there's one way to actually define or describe F3 geometrically. We are imagining that there's an elliptic Calabi-Yau space, X, as a total space, where the base manifold of this elliptic vibration is a base manifold B, which is a physical space where the strings really live in. And over each point on the base manifold B, we introduce an auxiliary 2 times T2, whose modulus actually equals to the value of axial dilettante field tau over that point. So generically. And then this whole space would be a non-trivial vibration over the base manifold that is described. It's an elliptic vibration, so that can be described using this kind of cubic equation, which is called the Weierstrass model or Weierstrass form. So in particular, x and y actually are complex coordinates that define a torus, while the coefficients ft and gt are functions of the base coordinate. So t here generally denotes the coordinates on the base b. Okay. Then what about the 7 branes? This is pretty interesting because the location of 7 branes will precisely correspond to the subset of the base manifold where the fiber is singular, and that is mathematically described by the solution set of the discriminant, and where the delta equals to 4s cubed plus 27g squared vanishes. This is equivalent to the previous monodromy description because over these points, the fiber is singular, which kind of means that actually the value of tau is not well defined over this point because if you go around it, the tau can be mapped to, for instance, tau plus 1 undergoes a non-trivial SL2Z monodromy. Yeah. So in a short sentence, the take-home message is that the information of the physical information of the configuration of 7 branes is actually encoded into the geometry of such elliptic Abel space in a very elegant way. Okay. And moreover, physically, the lower dimensional physical fields, such as the gauge groups, gauge fields, matter fields, and you call couplings, can be encoded using the open string from the open string sector connecting different stacks of 7 branes. Okay. All right. Then that was a basic introduction of what is string, what is F theory. Now the question is, how do we really build up string landscape in this geometric framework? So I list the 4 different steps of constructing F theory landscapes in general space-time dimensions. First, because as I said before, F theory definition of F theory model depends on the choice of an elliptic fiber Abel space. And the elliptic fiber Abel space has 2 different parts of information. The first one is that we need to choose the topology of the base manifold B, where really the strings propagate, the strings live in. And then, over such base manifold B, we also need to choose a particular type of elliptic vibration, that is to choose the form of our Weierstrass model or the coefficients F and G. In the algebraic geometry language, F and G are actually holomorphic sections of certain line bundles. So F is a holomorphic section of line bundle minus 4 times the canonical class of the base manifold B, while G is a holomorphic section of minus 6 times KB. Okay. And of course, you can choose a lot of different coefficients in F and G that will correspond to the complex structure moduli of your Abel manifold. Okay, X. So this choice of the elliptic vibration is equivalent to choosing our 7 brane configurations physically. So in fact, if you're only looking at 80 or 60 F theory, then doing this step 1 and step 2 are already enough to fully characterize an F theory supergravity model. However, if you want to really look into the real world physics, such as the 4D F theory, then in addition to the geometry and the topology, we also need to choose a discrete value of the so-called G4 flux, actually defined. The G4 is a G4 flux defined in the dual M theory picture, which can help you to actually compute or build up a scalar potential, effective scalar potential in your supergravity theory V phi I, where the phi i's are the moduli fields of your Abel manifold. And then you can imagine that the scalar potential V phi I is a very complicated kind of function over a huge parameter space, a huge moduli space, which is not flat like this. And after solving the local or global minima of this scalar potential, then we can stabilize all the moduli and even try to get some kind of ADS, Minkowski, or even Peter vacuum. So this is the whole story of basically building up theory geometric landscape. Okay. Yes. Yeah, also including Kähler moduli. also the D3 brane model in 4D F theory. So there could also be, I will not quite mention this in this talk, but in 4D F theory, due to the typo cancellation condition, then you generally a number of D3 brane floating around, in this internal space, which actually fills the whole four-dimensional Minkowski space-time. And these D3 branes can also contribute to a certain gauge group in your 4D theory, including U1 or even some enhanced non-abelian gauge group. But this will not be the focus of this talk. Yeah. So in this talk, when I talk about the gauge group, they are all come from the 7 branes. Yeah. Yeah. But generalization in F theory very limited, and in general, I don't believe in any of this precise calculation of any sort of 4D n equals 1 model generalization. Well, they are always up to certain assumptions. So this is the hardest problem in all the string phenol, basically. Okay, so now let's look into the step 1 and step 2. And in particular, I'll be focusing just on the mostly on the step 1, which is the classification of base manifold in this talk. So let's first look into the higher dimensional case, which is much simpler in terms of classification. For instance, if you want to get an ADF theory starting from 10D type 2, so the only choice to get an AD minimal supergravity is to choose a base manifold to be a P1, or topologically, this is just a two-sphere. And the X, the total Clapeyron space, is an elliptic K3 over the P1, which potentially some canonical singularities. So this is a physical picture where the base, this denotes a two-sphere. I didn't draw it in a nice way. And the red dots denote, so in general, there are actually precisely 24 7 branes located in this internal space, because here the Minkowski space-time already take up all of the 8 spatial space-time dimension of the 7 branes. So the 7 branes are actually just a point codimension, codimension to object on the base manifold. So a very classical result by Green, Shapiro, Baffa, and Professor Yao, actually this is a preclude of F-theory, I think, states that each of these 7 branes will contribute a pi/6 conical defect to your supergravity solutions. So in total, the conical defects equals to 4 times pi, which precisely match the topology of the base P1, the two-sphere. And so this is a case of a generic configuration of ADF theory. But of course, you can require that you can allow these different 7 branes to collide, which form some enhanced Caldera type of singularities on the elliptic K3, which you physically, if you have a stack of 7 branes colliding to a point, that will give rise to some AD non-abelian gauge groups. And here, this is a list of the Caldera type, well, not quite a singularity, but this is using the type of gauge groups. So each of these columns denotes the order of vanishing of these polynomials in Weierstrass model, IFG, and the discriminant locus delta. And in particular, the order of vanishing of this delta, this number corresponds to, it describes the total number of coincident 7 branes over a point. And here on the rightmost column, we list the type of AD gauge group using the algebra ADE symbol. And very interestingly, if the order of vanishing f and g and delta exceed 4, 6, and 12, it would mean that the elliptic K3 would have a worse than canonical singularity, something, for instance, like a log canonical singularity. And physically, this corresponds to, or mathematically, both mathematically and physically, this corresponds to the infinite distance limit of our complex structure moduli space. So actually, I think physicists already know about this very long ago. However, this was studied in more detail recently by Songzhu Li, Wolfgang Lersch, and Timo Weigand in the very famous paper. However, for general, most part of this talk, such kind of infinite distance limit with a worse than canonical singularity would be excluded in our F-theory landscape because, as they showed, this limit will generally correspond to some decompactified limit in, say, some kind of dual heterotic string, and it's not really a part of the ADF3 landscape anymore, precisely speaking. Okay. So that was the situation in ADF theory, which is relatively simple. So now, what about 6DF theory? If we want to compactify a type 2b on some complex surface to get 60 minimal 1,0 supergravity, then you may wonder what are the complex surfaces or the base complex twofold that you can choose. From the minimal model program, actually all the bases that can support an elliptic Clapeyron threefold with at worst canonical singularity lie into these two different classes. So they are either rational surfaces, which means that it's birational to a P2, or it can also be Enrique surfaces. But the second class is kind of uninteresting from the physics perspective. And the math and physical requirement is that over such base B2, we have to be able to construct a valid elliptic Clapeyron threefold that does not have a codimension 1, 4, 6, 12 singularity that correspond because that would correspond to our infinite distance limit. So for instance, such requirement could immediately exclude a lot of choices of B2. For instance, if B2 is a Hertzsprung surface where the n is bigger or equal than 13, then this is not allowed because any elliptic vibration over that, elliptic Clapeyron space over that would have such bad singularity. Okay? Yeah. Yeah. Yeah, terminal singularity are of course allowed, but this is worse than canonical singularity. Like this is actually log canonical singularity is not allowed in our program. You're talking about the terminal singularity is a, it's a much better type of kind of singularity than the canonical singularity. Yeah. Yeah, of course, terminal singularities are allowed. Oh, you mean terminal singularity on the base? No, so these are no, I mean singularity in the elliptic Clapeyron threefold, no, not on the base yet. Yeah, but in terminal singularity on the base also, well, because we are working, the base is a complex surface, complex two-dimensional space. So I mean, you only have a canonical singularity basically. Yeah, just a decompactified kind of limit in a dual frame. So it's not a, strictly speaking, it's not a part. It's not a part of the landscape anymore. Oh, Enrique surface, more or less. I mean, you can study them, but these are so. These are cases where the canonical class is a torsional, like 2 times k equals to 0. And the bad thing that, as I remember, you cannot really realize any interesting gauge group in this kind of model. So that's why we don't consider them. Because if you don't even have a geometric gauge group, then they're uninteresting from a physics perspective. But of course, you can study them if you wish. Okay, then now we are going to focus on the first case, which is a classification of all the smooth rational 2D bases for elliptic Clapeyron threefolds. And from the minimal model program, these are precisely come from the blowups of either P2 or Hertzsprung surfaces F with n less or equal than 12. And there are a lot of results in this direction, and in this number counting, we actually impose the following additional requirement that is not super necessary. But the requirement is that we also do not allow the quantum-dimension 2 612 singularities that correspond to some localized 61,0 strongly coupled ICFTs. So this is just a technical requirement for the better for better counting of this problem. Okay. So after we put additional requirement, there are serious results in this direction. For instance, Dave Morrison and Wang Taylor originally showed that, so they program, and they proved that there are in total more than 60,000 Tariq 2D bases that satisfy this condition. And 2 years later, they also showed that there are about 10 to the 5th different semi-Tariq bases, which are the complex surfaces with a single C star action. And then me and Wang Taylor, we constructed a sort of systematic algorithm for even generating a very general non-Tariq basis. Now, however, the lesson we learned from this study is that the following conjecture, I mean, not a very precise math conjecture, but it's a general feeling that the total number of non-Tariq complex 2D bases is not much more than the Tariq ones. So here we just plotted the number of these non-Tariq bases versus Tariq ones in various regions, for instance, in the figure on the left. So the horizontal axis is H11 of the 2D base. And as you can see here, the number of non-Tariq bases is not too much more than the Tariq ones. Now in the second picture, this number denotes the bases that can support elliptic Clavier threefold whose H11 is bigger than a certain value that can be pretty large. And also similar to the left case on the left, the total number of topologically different non-Tariq bases is not much more than the Tariq ones. So as a general lesson from this program, we found that the set of Tariq bases is a very good approximation of the whole set of base manifolds in F-theory. Okay. And physically, there's also another very interesting feature for a generic 2D base. It was found that there are a lot of forced gauge groups, which are the 60 gauge groups that are forced to exist from 7 branes wrapping some kind of rational curve C with a negative self-intersection number living on the base. Because, as I said, a 7 brane is a 7 plus 1 dimensional object, and we are living in a 6-dimensional Minkowski space, which means that the 7 branes should wrap a 2-cycle or complex curve of the base. So depending on the self-intersection number of the curve, sometimes a gauge algebra gauge group have to be forced to live on this curve. For instance, if you have a -3 curve on the base, it was proven that there has to be at least an SU3 gauge group living on the -3 curve from a stack of 7 branes, due to the non-zero negative curvature of the local region of that base. And also, for instance, if you have a -12 curve, then there has to be a E8 gauge group on the -12 curve. And it was found that by many people, this kind of phenomenon also generically exists in a 4D F-theory, which says that if you have just a general construction of 4D F-theory model in the middle of the landscape, it's already populated with a lot of these kind of so-called non-Higgsville gauge groups. So this is a physical feature that's totally determined by the topology of the base manifold. So that was a review of the 60 F-theory landscape. So now let's go into the more interesting case, which is the 40 F-theory landscape. And what we want is to realize at least a 40 n equals 1, the 40 n equals 1 supergravity in the high energy scale. And here we also need to probe what is the set. We need to study what is the set of the base complex threefold, B3. From the mathematical results in the minimal model program, it was shown that these bases can be either a blow up of a final threefold, or a blow up of some B2 fibration over P1, or P1 fibration over B2, where B2 is a complex surface. And a general condition is that as before, such base should be able to support an elliptic Clavier fourfold X4 with at worst canonical singularities. And of course, as Feng Jun asked, we allow the existence of terminal singularities. Yeah, that is fine. And then the question is, how do we classify this B3 in reality? It turns out that even if we are restricting ourselves to the subclass of Tariq-based threefold, it is still a huge set. Because as you can imagine, this is a recap of what is a Tariq threefold. A Tariq threefold B3 is defined by the combined Tariq data, including a set of rays, which are the 3-dimensional vectors living in an integral lattice, where each ray in this kind of Tariq fan would describe a divisor or just a convex surface, the submanifold of the B3, which can support on 7 branes with non-zero gauge group, as I mentioned before. And besides that, in the toric fan, we also need to specify the data of the set of 3D cones and 2D cones, which has to be compatible with each other. And this set of information would describe how does these toric divisors intersect each other. So as you can imagine, for a toric threefold is defined by this very complicated set of combinatoric data that consists of lots of different kind of rays in a 3D lattice. So there are a huge number of possibilities of choosing this kind of toric-based threefold. And the requirement that there's no dimension 1, 4, 6, 12 singularities can be translated to a very simple combinatoric criterion, which is saying that the origin 0, 0, 0 has to lie in the interior of the so-called dual G polytope defined in the following way that I will not spend more time to explain. Okay. Then you may ask, then what is the set of the smooth toric-based threefold that's satisfying the previous conditions? So over the years, there are multiple approaches that try to generate at least some subsets with a different kind of statistical or computational method. And as the time goes, this number will grow from 10 to the 5th to 10 to the 48, 10 to the 750, and also then to 10 to the 3000. So you really see a blow up on the exponential of this number of base threefolds. And interestingly, almost all the base threefolds would have some non-zero gauge groups, which can be interesting and relevant in the actual standard model building. So you may wonder what is the actual maximum number of such bases. And this question was answered in my more recent paper, which I constructed the certain base threefold with the largest H11, Hodge number H11 that can support the elliptic Clavier fourfold with the currently known largest H11 equal to 300, about 300,000. Yeah. So yeah. Yeah, it's a toric base. Yeah. Yeah, for non-toric base, we don't have a precise proof. However, this is, I mean, it's all conjecture. We don't have a rigorous proof. But just from the lesson we learned from the 60F theory, the ones with largest Hodge numbers are all realized by the toric bases. So that was proved, actually. Kind of proved. I think not precisely mathematically proved, but and this is a conjecture. It's a currently known largest Hodge number. Okay. So over this base, because it has such a huge Hodge number, it means that there are around 180,000 independent harmonic 2 forms, and which, if you expand the type 2B C2 field over these 2 forms, you get a huge number of axion-like particles that can be maybe relevant in some phenol kind of discussions. And as I said before, over this space, there exists a huge non-zero gauge group with 1,000 or 10 to the 1,000 of E8, I4, G2, and SU2 gauge groups. So in this 4D model, we got a lot of potential dark blue balls in our theory. However, the problem is that it's still unclear that how can we even realize standard model on such geometry, and this is still a hard problem now. Yeah. If you're interested, you can discuss later in detail, but I don't have time to explain this. Okay. So I also found that because this base threefold is so complicated, so many rays on it, you can imagine there's a huge number of different flip and flop faces just by changing the cone structures. So here I just show you a very tiny subregion of the base threefold where each dot, this big black dot denotes a toric divisor that can carry some gauge groups, and these little triangles denote a 3D cone. And because the structure of 3D cone is so complicated, you can imagine you can probably just change the set of 3D cones from this to this, and there are a huge number of ways to do this. So I proved that there are more than 10 to the 45,000 topological distinct bases just by manipulating the different cone structures. But basically, the lesson is if we treat all these topological different base threefolds as a different physical model, then the whole F3 landscape will be dominated by this particular geometry. But this really doesn't seem correct. And it's very possible that the counting of totally distinct 3D trig base is actually not a good measure of our whole geometric ensemble of F theory. But more recently, working with Wadi and a student, Yi, we propose an alternative approach where we treat all of these 10 to the 45,000 flip-flop faces of the same trig base as a single model, which drastically reduce this kind of redundancy, this flip and flop redundancy. And the good physical reasons behind this approach is that because all such models will have the same amount of gauge groups, same number of gauge groups, and the same G4 flux vapor, so they are roughly speaking kind of similar. Yeah. Okay. Because of one model, so it's like when we're doing the counting, we are actually just instead of counting the topological different trig threefold with a different 3D cone structure, we are treating these different 3D cone structures as a single model. So in other words, we are only counting the different set of convex halls of the trig rays, or the shape of this whole polytope, but disregarding the detailed triangulation or the cone structure. So we translate this problem to this volume math or even programming problem. So how can we classify all the different 3D lattice polytopes delta, that is a convex hall of all the trig rays, up to a GL 3D transformation that satisfy the volume math and physics conditions. And the conditions are similar to the ones I introduced before. For instance, we require that the origin has to be in the interior of the base polytope in order to get a compact trig threefold, and so on. And these are just a purely math or programming problem. However, the total number of such base polytopes is still too vast, and it is impossible to classify all of them. So in this new work, we actually use a Monte Carlo program to estimate the total number and the statistics. And actually, I need to make a further math detailed comment, is that if you are just giving me this base polytope, which is the convex hall of this space, then this one would not necessarily describe a smooth 3D trig base. So in fact, what we classify are the polytopes that can lead to 3D trig bases with at worst terminal singularities on the base. For instance, the weighted projected space P1112, this is already a good example. So actually, we probably allow the singular bases with these mild singularities. And as I said before, we does not distinguish different cone structures, and we treat all these flip and flop faces as one model in this improved counting. Okay, and these are some details, and basically what we do is we randomly sample a number of n lattice points in a fixed box, such as a box with the basis starting H11, or you can also choose another arbitrary kind of box as a wish. And each sampling will be chosen. We've chosen this kind of n points from this box, and so there are in total approximately this number of choices. If you in total do n samplings among which m of them are good, then we can naively estimate the total number of base polytopes to be the NC number of choices times this probability m over n. And this is the essential idea of a Monte Carlo program. However, this is kind of naive because there are huge redundancy in each of these choices, and we have to weight each of these choices by separate redundancy factor. And I'll not explain this in more detail. For instance, the permutation redundancy of these vertices. I will show you some result. If we randomly sample points inside the largest box, and we can vary the different number of random points that we choose and we sample. And we found that basically the total number of 3D base polytopes in the largest box goes up to like more than 10 to the 50, but not a very huge number though. We also compared between the different size of boxes. So this is like apart from the largest box, you can also choose to sample within some smaller boxes. And roughly speaking, the total number of 3D base polytopes are all like around the order of magnitude is around 10 to the 50, so not as big as the 10 to the 10,000 as I showed before. So these are kind of more, mild kind of estimation of this huge F-theory landscape. Okay. So what about the gauge groups? What about the gauge groups? In all of these cases, we found that the dominating kind of type of gauge groups are SU2, G2, I4, and E8. However, these are in generally not very interesting from the model building perspective. For the lesser, rarer gauge groups such as SU3 or E7 ones, we also plotted the estimated total number of gauge groups among different bases, and we found that this fraction will actually decrease as the H11 of the base goes larger. Yeah, so the horizontal axis denotes the H11 of our base threefold, while the vertical axis is the average number of each, say, E7 gauge group on each base. So as you can see, the number really goes down like this. And in particular, the case of E7 gauge group is interesting in the so-called E7 model building by the recent work by Xingyan Li and Wati Taylor about in this series of works. Okay. Because of course you can embed our gut SU5 gauge group in the E7 and also realize the chiral matter and so on. Okay. So that was a conclusion of the overview and some new results on the study of F-theory geometric landscape, and in particular the base landscape. So now for the second part of this talk, I'll be talking about the recent work with my student Lou Qinjian in the audience and also Shen Keren on the study of massive spectrum of F-theory. So as you may know, if you're an expert in F-theory, you know that actually in the existing literature of F-theory, the physical fields that people study are almost always the massless ones, including the graviton from the closed string sector, and also massless gauge fields, massless matter, and moduli field from either the open string sector or closed string sector. So in all the previous studies, people are focusing themselves on the massive spectrum. And then what about the massive states in F-theory that we can directly observe from a pretty high energy scale? So, of course, studying the massive states has a lot of physical motivations. For instance, these are relevant in the study and refinement of swan-plane conjectures, including the moduli distance conjecture and also weak gravity conjectures and so on. And physically, these massive states can also act as some dark matter or even standard model particle candidates, such as the Higgs field. Okay. So you may wonder, how can we construct such massive spectrum in F-theory? And of course, there are many types of such massive states. But the particular ones we study in this upcoming work is the following two types. The first ones come from the massive BPS string junctions that are stretched between a set of parallel 7 branes. This branes precisely means parallel 7 branes, not D3 branes. So if you have you can imagine if you have a stack of intersecting branes, then open string mode over it are always massless. However, if the two set of 7 branes does not intersect each other, then the strings or string junction in general connecting these two stacks of 7 branes will be massive. And you can evaluate the BPS mass of such string junctions by integrating the string tension over the string segment, over the string, and also minimizing the value, minimizing the mass m. And the second potential source for massive states in F-theory are also very simple. Of course, we will have KK modes from 10D type 2B superstring theory that compactified on the base manifold with a given metric. And this is a general story for any kind of compactification. We always get massive KK modes from this kind of dimension reduction, right? Now, first, in this talk, we'll restrict ourselves to the case of ADF theory because this is the simplest one, and the base manifold is just P1. And the particular configuration is that we are considering two stacks or two bunches of 7 branes that are approaching each other. And to simplify our result, and also in order to get some analytic result, we require that the value of axial dilaton tau is actually locally constant near these 7 branes. So basically the value of tau of these different stacks of 7 branes has to match. And then, the physical picture is like this, where we can have a bunch of 7 brains. So in this picture, I separate them into different points in a single box. And we also have the second bunch of 7 brains that's actually drawn by these big black dots. And if these two bunches are separated, they do not intersect each other, we have a certain number of PQ strings stretching between them. So this is the string junction configuration we are looking at in the paper. And finally, in the non-abelian gauge theory limit, where all the brains, so this can be thought as some Higgs space. If we then collide all the 7 brains in a bunch to a single dot, we get the following picture, where precisely the BPS condition that minimize the BPS mass will lead to such configuration where all the PQ string from L1 to Ln are along the geodesic connecting these two stacks of 7 brains. So this picture, roughly speaking, looks like just a single open string between two different D brains, but actually it's more complicated because it's really a string junction, and each of them L1 and Ln would have a different value of P and Q. Yeah. Yes, for the case of a locally constant activity on tau. So under the assumption that the taus are basically constant around this place, in the neighborhood of this. Well, we know in ADF theory, we know. Yeah. This is the point of studying ADF theory. So we know the metric. This is why we can do this computation. Okay. And then in particular, I mean, we have more details in this upcoming paper, but a very interesting limit is actually when two bunches of 7 brains are colliding into a codimension 1 4 6 12 singularity. For instance, the two stack of D4 brains with isoic gauge groups, if you collide these two stack of brains, we'll get a codimension 1 4 6 12 singularity leading to an infinite distance limit in the complex structure moduli space. So we parameterize these two different stacks of 7 brains. So one stack is located at t equals to 0, where t is a base coordinate, and the second stack locates at t equals to t1. And after a computation, we actually get a very nice analytical result. So the mass of the BPS string junction takes the form of, so this is just some numerical factor, you can ignore them. And it's taken the form of a square root of the volume of P1 over the log of this distance T1. So T1 is basically, you can think about it as a coordinate in the complex structure moduli space. So, roughly speaking, if the T1 goes to 0 and they collide into this codimension 1 4 6 12 singularity, the absolute value of log T1 is actually becomes infinitely large, right? So this goes infinitely large. Actually, the mass of BPS string junction will be infinitely light in this colliding limit. Yeah. And this is actually pretty much expected because, I mean, it's not so naively you can just think about that if you have two colliding set of brains, then of course the distance between these two bunches of brains will become shorter and shorter, right? And you can expect the mass to be vanishing, but actually you need to really do the computation carefully, since you need to normalize the form of metric if you want to fix the Kähler moduli at the volume of the whole base P1. So this is a non-trivial calculation. Okay. And then in this nice paper by Songzhu, Wolfgang, and Timo, they discussed that in this particular codimension 1 4 6 12 limit, the elliptic K3 will have a type 2a Kulikov degeneration. And in this case, the dual description in the infinite distance limit will be a decompactified 10-dimensional heterotic string on a large T2, where the volume of T2 goes to infinity. Hence, the heterotic side, they predict the existence of an infinitely light tower of KK modes from 10D on this very large T2. So our light string junctions are precisely the candidate of such infinitely light tower states on the absolute side. And we kind of verify their prediction in this sense. However, after a careful calculation by matching the metric of moduli space on the hydraulic side, we found that the mass of such Lie tower of states are actually taken in this asymptotic form. So on the so this delta S is a distance in the properly normalized moduli space. And in fact, his numerical factor square root 3 over 8 actually does not match the expected factor that's square root 2 over 3 from the KK reduction of 10D to 8D. And our explanation of this discrepancy actually potentially comes from the issue or the subtlety in the definition of the 80 Planck mass on the strongly coupled F-theory side. Because on the hydraulic side, this can be obliquely coupled, and we have a good definition of the Planck mass. However, on the F-theory side, it's strongly coupled, and we don't really know what are the large quantum corrections theory effective action. And we make a conjecture that if on the F-theory side, the 80 Planck mass scales as MP proportional e to this numerical value, then these two results would match. And our string junction tower that we found would actually match their prediction, but only up to this conjecture. Yeah. So this, I think this is our actually new prediction from this study. It's a new result in the strongly coupled F-theory slide. Okay. Then, besides the string junction states, as I mentioned, we also firstly try to compute the set of massive KK modes in ADF theory, only in a very limited subset, using the known metric of the base P1 that's already existing in literature by the people Green, Kasbafa, and Professor Yao. So we know people know this singular metric of a base P1 already pretty long ago, and the idea is to just consider KK mode from a dimensional reduction of some 10-dimensional fields, such as the two-form gauge field, and we expand the two-form gauge field to this 2 plus 8 dimensions in a particular using a particular ansatz, which is that we separate this B2 two-form gauge field into a scalar in the internal space on the P1, and also a massive two-form tensor field in the 8-dimensional Minkowski space-time. And then we use a dimensional reduction of the 10-dimensional leading order kinetic term for this two-form gauge field to solve the equation of motion for the actually little BI, and then expand the BI in terms of the spherical harmonics on the base 2 sphere. And then numerically, we can solve an eigen problem to get all the KK modes. So as before, we also consider two boundaries of 7 branes colliding into a codimension 1 for 612 singularity that are located at t equals 0 and t equals t1. So after numerical study, we found this KK spectrum whose mass has this qualitative, actually quantitative result like this, where the lambda i's, square root 2 pi lambda i's of the lowest KK modes are listed in this figure. So from this result, actually very interestingly, the KK modes, the mass of KK modes will become infinitely heavy in the infinite complex structure moduli limit where the T1 goes to 0. So we can basically kind of ignore this KK modes on the F-theory side, actually in the infinite complex structure distance limit. Yeah. But this is also a new result, I think. Okay. So finally, let me conclude my talk. In this talk, I mentioned two ongoing works after general review of the 4D F-theory landscape. The first one is we're working on a better measure for the base threefold ensemble in 4D F-theory that is more kind of reasonable than the previous approaches. And secondly, we present the first study of massive spectrum in F-theory directly and discussed the relation, the relevance to the infinite distance conjectures. And of course, in the field of whole F-theory, there are still a lot of open questions despite more than 20 years of development. For instance, first, considering the different topology, the different geometric construction, or the whole base ensemble, the important question is to study what are the physical procedures behind this topology transition of different bases. And of course, the most interesting question in whole F0 in the whole string phenol is that how do we even compute the precise form of the superpotential or Kähler potential, and then eventually the scalar potential in 4D F0. And only by doing this can we really achieve a good modulus realization discussion in F theory, and then discuss maybe the mechanism behind the SUSY breaking scale. Also, how do we realize the de Sitter vacua in F theory? Yeah. Thank you very much.
Have any questions for Yi-Nan?
Can you go back to this? You said the strong capital F series Planck mass
yes,
should be. Oh, yeah. So usually we say that at least even for the strong capital F series modulus, the Planck scale mass it doesn't change, right? What do you mean this change with respect to what?
So this is like with respect to the naive. So naively, you may say that. So how do we determine the Planck mass from a dimensional reduction?
Yeah,
usually you just dimensionally reduce the 10-dimensional Hilbert term on your internal manifold, right? And then use the volume of the internal manifold to compute your Planck mass. It's the Euro story, right? However, we suspect that it's not a rigorous proof. But in this particular limit, because actually it's really strongly coupled, there's a very huge quantum correction to this lower dimensional or even 10-dimensional action. And as a consequence, the approximation of just treating the leading order Hansen-Hilbert term is probably invalid. And we need to introduce with further corrections to a Planck mass that's related to the to your location in the moduli space. So, and this is still a conjecture.
Okay.
Yeah, because as you can imagine, the F series is not simply by reducing a 10D type 2B just on a P1, right?
But usually you can use in a duality with M series, right? M series compact on K3, then gives a 6D Planck mass.
Yeah, that's right. Yeah, we are really, really working in a region that's already close to a dimension 1, 4, 6, 12 singularity. And in this sense, the M series dual picture also could break down. Yeah. So actually the rigorous way is to study the hydraulic dual side. In the hydraulic side is strongly weakly coupled, so the computation is valid. However, people, I think in the literature, nobody really know the precise duality between F0 and hydraulic in this case.
So would you say that this is a result of renormalization of Newton's constant?
Yeah, you can also interpret it as this.
Because you have a bunch of light fields, so you expect it to be renormalized.
Yeah, probably, yeah. There are long quantum corrections from the light field. Yeah. So this, infinite distance is at an infinite distance you expect the effective action to be breakdown, to break down, right? Yeah.
So when you calculate these KK modes, you using this type 2B and Sugra?
Yeah, just a type 2B Sugra, the leading order term. So this is not a very precise.
Yeah, because usually you don't have a certain limit for this series.
No, it's don't necessarily have a certain limit. Yeah, and in particular in this limit, but we generally expect the qualitative feature to still hold. Although these coefficients are probably not precise. So these are using some very crude estimation.
Okay, do we have any more questions?
Yeah, here.
So in this part, I know you use a metric and you can solve this mass by solving this eigenvalue function.
Yeah.
But when you go to this large complex structure limit, but the mass just become infinitely large, it should become massless?
It's fine. I mean, usually the KK mode becomes infinitely light when the volume of the P1 goes to infinity, right? And this is still hold. So if the volume P1 goes to infinity, this becomes infinite light. So, but nobody discussed the relation of KK mass with respect to the complex structure model. And this is just what we found.
I see.
Okay, any more questions? If there are no more questions, then let's thank Yi-Nan for a very nice talk.
Thanks.